The winter of 1815 was fairly standard. It wasn't particularly warm or particularly cold. In England, the snow fell, the trees were bare, and no doubt people would stare out of their windows waiting for the spring to arrive. The problem with the winter of 1815, though, was that it just failed to end. 1816 became known as the year without a summer. Average global temperatures dropped around 0.4 to 0.7 degrees centigrade. New York State, Maine and New Hampshire had a record snowfall in June, with Quebec City getting a fall of 30 centimetres. There were late frosts and crop failures in the United States, Canada and Europe. The growing season of New Hampshire would drop from 120 to 60 days. In Ireland, wheat, oats and potato harvest failed, and with this came famine and an associated outbreak of typhoid that killed around 60,000 people. The weather will be driven to extremes. High rainfall in some areas and drought in others. In Switzerland, the months of April through August, some 152 days, record 130 days of rain. In India, the monsoon was disrupted, leading to floods and droughts. 3 harvests would fail, and famine was close on the heels of the crop failures. It is thought that these famines would see the development of new strains of typhoid and cholera, causing even more misery and death. The 1816 year without a summer would have other effects too. Consider this famous painting, Chichester Canal by J.M.M. Turner. Beautiful, isn't it? But it is just one example of many fantastic sunsets, when the sun was actually visible, that would be painted by artists that year. That strange summer didn't just impact painting though. With the exception of sunsets, days were pretty gloomy, and this would act as a literary inspiration for some. For example, Lord Byron and his poem Darkness in 1816. One Mary Shelley was travelling with Byron and other friends during June through Switzerland. As we noted, Switzerland was rained out in that summer, so with nothing else to do but stare out of the window at the rain, they decided to have a writing contest to see who could come up with the scariest story. Mary came up with a touching little Gothic piece called Frankenstein. In general, the climatic gloom, failure of crops and the spread of famine and disease were taken by many to be caused by immorality and low church attendance. Many thought that the apocalypse was just around the corner. What could have caused such a cascade of events and drive so many people into famine and disease? A clue comes from Sir Stamford Raffles, a British statesman best known for founding Singapore, who of course lent his name to a very famous hotel in that city, where, if you have the inclination, I did, not just once, you can indulge in the original Singapore sling. He also lends his name to Rafflesia, a giant flower with a rotting flesh stench that is considerably less appealing than a Singapore sling. In his memoir, Raffles reports hearing explosions while he was on Java on April 5, 1815, that were at first mistaken for the sound of a distant cannon. The source of the detonations was not man-made though. They came from the island of Sumbawa, and specifically the eruption of Mount Tambora. On April 10th, the eruption reached its climax, with explosions heard over 1,600 miles away on the island of Sumatra. In total, over 138 cubic miles of material were ejected by the eruption. For comparison, the more famous eruption of Krakatoa in 1883 would only release 6 cubic miles of material. The Tambora eruption would kill around 88,000 in pyroclastic flows and tsunamis. It is also the cause of the year without summer. It would achieve this through processes we have met before in this series. The ejection of fine ash into the atmosphere would dim sunlight. Large volumes of sulfur dioxide would generate various sulfate aerosols and sulfuric acid that would further dim the planet and contribute to the destruction of ozone. These effects were compounded by the fact that the eruption occurred during a period of low solar output, a Dalton minimum, which caused shifts in weather patterns. Deep troughs developed from the poles, causing monsoons to fail, and droughts and floods as well. Ash and aerosols would paint lurid sunsets in the sky. Estimates vary, but it's thought that hundreds of thousands of people would probably lose their lives as a consequence of the climatic effects of Tambora. Tambora was one of the greatest volcanic events in recorded human history and had devastating effects far beyond Southeast Asia. Even so, there was no mass extinction recorded at this time. Geologically, this was a minor event. In this final episode, I would like to ask, what does the future hold for our species, and what role does paleontology have to play in this inquiry? So let's ask, have Homo sapiens already nearly suffered extinction? What are the likely causes of change to the Earth system in the future? Why is paleontology still relevant? And just where is paleontology going? Have you ever noticed how different we all look? Different facial features, skin colours, statures, a tapestry of humanity, all very different, a staggering diversity. You might be surprised to learn that some claim that there may be more genetic variation in a troop of chimps than there is in all our species. Some take that even further. If you consider the genetic variation between two individuals in neighbouring tribes in East Africa, you will find more genetic variation between them than between, for example, any person from Western Europe and anyone from Southeast Asia. Counterintuitive, right? This idea comes from the studies of mitochondrial DNA, the little power units within our cells that have their own independent genetic material that can be used to trace human lineages through time. It has been suggested that mitochondrial DNA records may indicate that the population of Homo sapiens dwindled to around 2,000 to 5,000 individuals living in East Africa around 50,000 to 100,000 years ago. This is called a human population bottleneck and was claimed to account for the low genetic difference that exists between human beings. So, how do bottlenecks work under this hypothesis? Consider human population before the bottleneck event, as represented by this bottle with coloured marbles, consisting of diverse and varied genetic populations. Now take that bottle and shake out some of the marbles. As you will see, not all the marbles will get out. This is our bottleneck event. If we now place the marbles that escape the bottleneck into another and allow them to repopulate, we produce a population that is now less genetically diverse than the pre-bottleneck population. This represents the current East African population. Now take a sample of that remaining East African diversity. This now represents the fraction of that genetic diversity that would spread through the rest of the world, which is why all other peoples outside of East Africa would have much less genetic diversity than the population in East Africa. It has been proposed that this is how we end up with such a restricted human diversity today. But what was the bottleneck? What was it that could have caused such a reduction in the diversity of our species? For a possible culprit, take a trip to the poles. A sample of any material that ends up in the atmosphere ultimately gets preserved in the snow and ice at the poles. By studying gas bubbles trapped in the ice, we can look back in time through climate history for some 800,000 years. What we find is a spike in sulfuric acid representing 2 billion tonnes of sulfur dioxide, concentrations that can only be volcanic in origin. For comparison's sake, consider the eruption of Pinatubo in the Philippines in 1991. This released 22 million tonnes of sulfur dioxide into the atmosphere, causing a global temperature drop of around about 0.5 degrees centigrade. Although this might sound like a minor change, it is thought to have halted global warming for 1 year. Obviously, if we have 2 billion rather than 22 million tonnes of sulfur dioxide, that suggests something much larger than Pinatubo. We do have a candidate, and for that we look to the Indonesian island of Sumatra and the Lake Toba volcano that erupted around 75,000 years ago. If you were to travel to Toba, you would be hard-pressed to find evidence of a volcano. You will find the lake, of course, but no familiar volcanic cone. This is because Lake Toba is the volcano, or at least the shattered remnants of one. To get a handle on the sheer scale of the Toba eruption, it is helpful to consider what is known as the Volcanic Explosivity Index. This is a kind of a volcanologist's Richter scale that considers the total volume of material erupted explosively. The scale is ranked from 0 through to 8, with each point on the scale from 1 upwards representing 10 times more material ejected than the previous point on the scale. A classic example of a VEI-1 eruption would be Kilauea on Hawaii. Eruptions here are what we call effusive. The basaltic magma that produces these volcanoes is fairly runny, in part due to its low silica content, which permits gases to escape easily and generally emerge non-violently. It produces features such as lava fountains and sometimes rapidly moving lava flows. Viscosity is critical to the character of a volcano. Consider these 3 liquids demonstrating increasing viscosity or stickiness. Relatively, milk would be low viscosity, followed by honey, and then peanut butter. A basalt would be on the milky end, if you want, of this relative scale, but some magmas are definitely of the peanut butter variety, a result of the higher silica content. Gas dissolved in the high viscosity magma cannot escape as easy as it can from the low viscosity magma like we see in Hawaii. So what happens to all that gas in a volcano with viscous magma? As the magma rises through the volcanic feeder pipe, its pressure drops, which allows the gas to come out of solution, all at once. The gas bubbles grow in an instant, and when they touch, they fragment the magma in an explosive eruption. This is how volcanic ash is formed. This is the type of eruption that occurred on Sunday, May 18, 1980 at Mount St. Helens. The event generated an eruption column that rose 15 miles into the atmosphere and deadly pyroclastic flows of hot ash and gas travelling at 670 miles an hour along the ground surface for over 23 miles. But this is still only at 5 on the VEI scale. For a VEI of 6, think Vesuvius during AD 79. This was a similar type of eruption to Mount St. Helens, but with 10 times more material explosively erupted. The destruction of Pompeii and Herculaneum would see around 16,000 fatalities. Krakatoa, the largest noise in recent human history, is also VEI 6. So what of Toba? Well, have a look at this diagram representing the relative volume of material produced in volcanic events. Here is St. Helens at VEI 5. At VEI 6, examples include Pinatubo in 1991, Krakatoa in 1883, and Vesuvius during the early Roman Empire. Then there is Tambora in 1815, the eruption that caused a year without a summer, 10 times greater than Vesuvius at VEI 7. And what of Lake Toba? Well, Toba is VEI 8 and would erupt over 2,800 cubic kilometres of material. This is why Toba is known as a supervolcano. Toba produced pyroclastic flows that covered 18,000 square kilometres and generated an ash cloud 80 kilometres high. Some have claimed that Toba would have sunk the planet into a global winter over 6 years long. Could it be this that nearly wiped out our species from the surface of the planet? Similar genetic bottlenecks have been suggested for other species such as cheetahs and tigers, the Bornean orangutan, certain gorilla populations, and the central Indian macaque around 70,000 to 55,000 years ago. But this remains a controversial hypothesis. A more recent research has cast doubt on the link between Toba and the proposed human bottlenecks. For example, there have been problems with the timing of the proposed volcanic eruption and the onset of environmental changes in East Africa. Researchers have identified materials from Toba in the sediments of Lake Malawi, indicating that the fallout from Toba travelled a considerable distance. However, there is no indication of significant climate change following the eruption. Other significant problems in the hypothesis have come from archaeological stone tools in India that have been recovered from both below and directly above the Toba ash deposits in that country. Not only do the stone tools suggest a continuity of habitation, but there is also a continuity of technology as well. It is also important to note that other hominid populations, Homo floresiensis and Homo neanderthalensis, successfully made it through the Toba catastrophe. Although popular in the late 90s and early 2000s, many have now moved on from a bottleneck in relation to the Toba eruption, demonstrating how new discoveries are continually shaping our insights in the Earth's past, even challenging and dismissing sometimes hypotheses that might appear very neat and appealing at the time. What the Toba eruption does highlight, though, is the fact that catastrophic events are not just a feature of the deep past. Our planet is a continually evolving dynamic system where things generally happen at a fairly, geological pace most of the time. This slow background pace is peppered with rapid events that can cause dramatic and sometimes catastrophic events, as we have seen in this series. Even if Toba did not have a significant impact on numbers of humans 75,000 years ago, if Toba were to occur today, with all our vast population reliant on limited food resources, it could be catastrophic for human civilization. So what are the likely causes of change to the Earth system in the future? Obviously, this is difficult to predict. The continents will continue to move about our planet as they have for billions of years. Reconstructions like those of Christopher Scotese from the University of Texas at Arlington predict that a new supercontinent will form in about 250 million years from now, part of a supercontinent cycle like the beating of a heart. But as we have seen, printed on the slow movements of the continents are rapid events like Toba, a volcano which itself is far from extinct, with indications that the magma chamber is currently refilling. Although, as there is currently no surface movement, it would be a long time probably before we see another eruption. Toba is not the only supervolcano candidate, of course. Closer to home, we have Yellowstone, another volcano that is so vast that it is difficult to appreciate that it actually is a volcano from the ground. Yellowstone is a caldera 60 by 32 kilometers across, which last erupted in a VEI-8 about 640,000 years ago. Yellowstone, unlike Toba, is breathing with the caldera floor rising and falling, probably in response to the developing magma chamber below. Like Toba, a major eruption at Yellowstone would likely be catastrophic for human civilization, but even with the park's ups and downs, it is thought that it is unlikely to erupt anytime soon. Other sudden events can strike from the skies rather than rising from the depths. Paleontologists and geologists have been studying the violent end of the Mesozoic biosphere 66 million years ago for decades now. The general consensus is that the Earth was hit by a 10-kilometer diameter object that caused such catastrophic environmental change that it drove the Mesozoic biosphere, including the dinosaurs, into extinction. Just recently, we have been reminded that impacts from space, like major volcanic events, are still a very reasonable part of our collective future. On the 15th of February 2013, at around 9:20 a.m., a bright light was seen streaking above the skies of Russia. The event was captured by CCTV and dashboard cameras all over the southern Ural region. It was caused by a 20-meter diameter object, entering the atmosphere at a speed of around 40,000 miles per hour. As a result of its high speed and angle of entry, the object exploded 18.4 miles above the ground, generating a shower of fragments and a significant shockwave. The energy released in this event was equivalent to 500 kilotons of TNT. That's around 20 to 30 times more energy than the bomb detonated at Hiroshima. The event damaged over 7,000 buildings in 6 cities. About 1,500 people received injuries, mostly from broken glass that required medical treatment. If this object had hit the ground, it would have generated a substantial crater and probably more damage and potentially more fatalities. Not a mass extinction level event, but it certainly shows that the days of impacts from space, just like supervolcanoes, are far from over. Another important vector of change in both our short and long-term future is climate change. The now famous Keeling curve that shows the yearly changes of carbon dioxide at Mauna Loa in Hawaii beautifully reflects seasonal variations in the uptake of carbon dioxide by plants over a year. Of course, the most startling feature of the data is the increase in carbon dioxide levels over time. These results, placed in the context of a deeper time perspective, show how current changes in carbon dioxide levels cannot be explained by natural ice age cycles. The increase in global temperature will impact sea level, climatic patterns, species distributions, and a whole range of other potential effects that we can't yet predict. There is a scientific consensus on climate change stating that climate is changing and that these changes are in large part caused by human activities. We are also witnessing a drop in global biodiversity. As with the extinctions we have studied in this series, there is often a trigger followed by a cascade of events that cause the actual extinction. Today, as in the past, the cause of these extinctions is varied: climate change, habitat loss, and pollution, to name but a few. And the trigger? Well, the trigger this time appears to be us. With all these changes to the Earth system, there has been a call by some geologists and paleontologists for the erection of a new geological period, the Anthropocene, to reflect these changing times. In 2008, the International Commission on Stratigraphy received a proposal to make the Anthropocene a unit of the geological timescale. There is some debate as to when and how the actual boundary will be drawn. Some favour an early boundary around the Neolithic Revolution, which saw the transition of many human lifestyles from hunter-gathering to one of agriculture about 12,000 years ago. This, though, kind of places it in conflict with a pre-existing period, the Holocene, that begins about 11,700 years ago and continues to the present day. Others favour a more recent definition based on atmospheric evidence of the start of the Industrial Revolution in the late 18th century. It has been suggested that the Thomas Newcomen steam engine, the first practical use of coal and steam power used to drain mines, marks the very start of the current changes we are witnessing. That would place the base of the Anthropocene sometime in 1712. So, with all these changes occurring in the present, why should we be dreaming about the distant past? Paleontology is obviously engaging. It has been called the gateway science by many who see fossils as a hook to intrigue children about the wider world of science. It is also still very important to industry, particularly in the context of biostratigraphy for mineral and hydrocarbon exploration. But is there any other reason why our tax dollars should be spent on paleontology other than it's fascinating? I personally think it's fascinating is a good enough reason on its own, but then I would, wouldn't I? But I believe paleontology is also vital in these times of rapid change in the Earth system. Paleontology and the wider disciplines of geology and biology on which it rests are the only areas of science that can provide context to current changes. James Hutton, the father of modern geology, in his paper concerning the theory of the Earth in 1778, concludes, "The result, therefore, of our present inquiry is that we find no vestige of a beginning and no prospect of an end." This idea that the past could be interpreted by understanding processes going on in the present would allow for a revolution in the investigation and interpretation of rocks and fossils. A famous 18th century geological superstar, Charles Lyell, who was heavily influenced by Hutton, would state, "The present is the key to the past." But we can turn this around, can't we? For as we have seen in this series, the biosphere has moved through many interesting times. It teaches us that change is perhaps one of the few constants that we can rely on in Earth's history. As we have seen, change always comes tapping on the door even after millions of years of stability. So perhaps we can paraphrase Lyell. Perhaps the past could also be the key to the future. By understanding the vectors of slow changes in climate caused by the shifting continents, or sudden catastrophic change caused by extreme volcanic activity, or impacts from space, and by recording the reaction of the biosphere to these changes as preserved in the rocks and fossils, we can grasp at that vital context we need to fully appreciate current changes in the Earth system. For example, as we mentioned earlier, it is accepted that we are in a downward trend with regards to biodiversity, a trend of extinctions that is greater than the usual background rate of extinction that we would expect in the biosphere. The vital question is whether the current trend is far less, the same, or in excess of the loss of species that we know occurred in the Big Five past extinction events. This is a fundamentally important question, and one which only paleontology and biology can really answer. Our understanding of the rates and extent of the Big Five mass extinctions are continually being refined and updated as new geological techniques, sections and fossils come to light. A fine example of this is the end Permian extinction, which, until recently, was a relative mystery. Now we are gaining insights into the triggers, the cascade of ensuing events, the timing and the extent of this mother of all extinctions. In 2015, a team of scientists, including Paul Ehrlich of Stanford University in California, suggested that we may be moving towards a mass extinction event. The study considered past rates of extinctions so that they could be compared to current changes in biodiversity. To address criticisms that previous studies about current extinction rates were flawed, they selected what is considered to be a very high estimate of background extinctions between the Big Five mass extinctions. The results they generated suggest that current extinction rates may be 100 times higher than the assumed, probably artificially high, background rate. With their calculated extinction rate, we should have seen around 9 vertebrate extinctions since 1900, but 468 more documented vertebrate extinctions have been recorded, including 69 mammals, 80 birds, 24 reptiles, 146 amphibians, and 158 fish. Of course, we may be unaware of other species going extinct because they have vanished before we could find them. If these estimates are correct, then these are disturbing trends. The study claims, though, that with conservation and proper environmental management, these trends could be reversed. I think paleontology has a vital role to play in these efforts. It speaks to the time and pattern and recovery of ecosystems after extinctions, and also to the minimum level of biodiversity required to maintain a healthy biosphere. It also provides a warning, as we noted for the end Permian extinction, regarding how rapidly the biosphere can be plunged into crisis. Ernest Rutherford was claimed to have said, "All science is either physics or stamp collecting." I hope I have demonstrated how untrue that is for paleontology. While the classification and taxonomy of fossils is vital and underpins paleontology, the science that we do now upon that bedrock is both amazing and fundamentally important. But what of the future? Where will paleontology go? As I have said, paleontology has an important role to play in the understanding of the past, present and future of our planet. We have probably only uncovered a minute fraction of the wealth of information that is held in the Earth's crust. You only have to scan through a paleontology journal to see the rate at which new finds are challenging and changing our views of the history of planet Earth. This, in combination with new techniques for studying fossils, is going to open up new perspectives of our planet and its 4.54 billion year journey through time. But is there another direction for this science? Perhaps that step has already been made. The supposed bacteria-like fossils described in 1996 on the Martian meteorite ALH 84001 have remained elusive, with no definitive evidence that these structures are the product of a Martian biology. Even so, this really did start to take paleontology beyond our home planet. For the first time, paleontology had to seriously consider the possibility of fossil life from another world. More recent research regarding the possibility of fossils on Mars was published in 2014 by Nora Noffke of the Old Dominion University in Norfolk, Virginia. Nora is an expert in ancient microbially induced sedimentary structures, or MISS. not unlike the stromatolites produced by biofilms that we mentioned in an earlier episode. A particular set of photographs taken by the Curiosity rover caught her attention. They were taken in an area called Yellowknife Bay in a dry lake bed that may have gone through seasonal flooding around 3.7 billion years ago. What she noticed were particular domes, cracks and pitted structures that looked very familiar, structures that she had seen before in ancient myss structures from Western Australia. She admits that it is possible that these features could have been produced by erosional processes of salt, water or wind, but they do strongly resemble the ancient myss from Earth. To be honest, determining the biogenicity of ancient microbially induced sedimentary structures on Earth is difficult enough, so making determinations from photographs of Mars is speculative, but still intriguing. The only way to sort this out for sure would be to go there. This is why the first missions taking humans to Mars will most likely include a geologist, and at the very least, a geologist with a lot of paleontology and biology under their belts. Whether or not these structures turn out to be fossils, paleontology will likely be one of the key tools in determining the possibility of life elsewhere in the universe. So what is the future of paleontology? Perhaps universal. With new exoplanets being found around stars every year, who knows where a future fossil hunter may tread? And the future of museums like the Smithsonian's National Museum of Natural History? Far from an institute of paleontological stamp collectors, the museum is a hotbed of cutting-edge research, charting the history of Earth's systems through time. It is in places like this, and others around the world, that the keys to the past, present, and the future will be cast, and with them, perhaps a more secure future for us all.